Okay, so hello everybody. Good morning and good night and good evening, good afternoon. So welcome to One Word Mathematical Physics seminar. So this is the final seminar of this very special year, 2020. And it is our great pleasure to have Yoshiko Ogata. And before that, I have to make an announcement. So you can ask questions during the talk. And you can either use chat, write your question in chat box, or you can unmute yourself and ask directly. Otherwise, please always mute yourself. Okay, so now we have Yoshiko Ogata, and I think all of you know that she's one of the leaders in mathematical physics of quantum many-body systems. And today she announced to give a talk about classification of symmetry protected topological phase, whatever, in quantum spin chains. But now you see that her title has changed. And I hear that she is going to tell us about something very new. So we are very lucky to be here. I think this is historical. So I'm looking very much forward to this. So Yoshiko, could you start?
Thank you very much. Thank you very much for the introduction. It makes me a bit stressed. But
I'm sorry.
I'm going to talk about, first of all, thank you very much for organizers for giving me this opportunity to talk here today. I'm going to talk about classification of symmetry protected topological phases in quantum spin system. So I'd like to start this talk by explaining what is symmetry protected topological phases, so-called SPT phases. So in this business, what we consider is the following set of Hamiltonian. First, the Hamiltonian has a unique gapped ground state. Namely, we call it the Hamiltonian should have unique ground state, and there should be a gap, spectral gap between the ground state energy and the rest of the spectrum. And second, it should satisfy some given symmetry beta. And third, this Hamiltonian should be can be smoothly deformed into some fixed trivial Hamiltonian. Trivial means on-site Hamiltonian without facing a phase transition. That is a kind of that is a condition. And what we are interested in SPT business is Hamiltonian satisfying these three conditions. And but we would like to classify such a set of Hamiltonian, and we would like to classify them with the following criterion. That is, two Hamiltonians are equivalent if they can be smoothly deformed to each other without a phase transition. And what is important is, in addition, we require the symmetry to be preserved. That is the requirement, and so we require along the path the symmetry do not get broken. So that is the requirement, and this is a classification we consider. We would like to consider about this set of Hamiltonians. And as a result, we get some equivalence class or phases, and these resulting phases are called SPT phases. That is, and this talk is about this SPT phases. So this talk is about, more precisely, I talk about classification of SPT phases in a spatial dimension 1 and 2 dimensional quantum spin system with on-site finite group symmetry. That is what I would like to talk about in this talk. So in order to, that is the kind of problem I'm interested in, but in order to think about this problem, I would like to think about this problem in operator algebraic framework of quantum statistical mechanics. Namely, instead of considering finite system and take the thermodynamic limit, I would like to start immediately by considering infinite system from the beginning. The reason for doing that is the following, that is, I'm going to define some index which is invariant of the classification I consider, And this index can be most naturally defined in infinite system than considering finite systems. And the situation is pretty much analogous to the situation of Fredholm operator. Recall that a Fredholm index is 0 for any operator on finite system. And but so in order to get some interesting Fredholm index, which is not 0, you have to go to infinite system. And pretty much analogous thing is happening there, I think. So for this reason, I would like to consider this problem in operator algebraic framework, which allows us to treat infinite system. So I would like to, I will do that for the rest of the talk. So in order to do that, first let me explain the framework. First, the framework is like this. First, our quantum spin system is given as follows. That is a infinite tensor product of d by d matrices along no-dimensional lattice. So here, d indicates the spin, the size of the spin, and nu is a spatial dimension. So no-dimensional quantum spin system is just simply just this infinite tensor product. And for each finite subset gamma, we can associate a tensor product of d by d matrices along gamma, and we denote it by a gamma, and this can be regarded as subalgebra of this whole quantum spin system. So we do so, and And in addition, we consider we collect all the elements in quantum spin system with finite support and call the set a local algebra, and I denote it by a local there. So that is the notation I use in this talk. And a physical model in this framework is defined by interaction. And interaction is a map. It's mathematically defined as follows. It is a map from the set of all finite subset of no-dimensional lattice to this local algebra, which satisfy this condition. Namely, for each finite subset X, we assign some element from a local algebra, but it has to be self-adjoint. It has to be localized at the region X.
So we have a question from Brother Yoruba, who is raising his hand. Sorry,
Yes.
Mr. Chairman.
Yes. So can you clarify what is this infinite tensor product of sister algebras precisely?
It's inductive limit of the finite tensor.
So it's the closure with respect to some sister norm of this local algebra.
Yeah. Is it okay?
Okay. It's better to use chat for questions like this. So please, but anyway, thanks.
Okay, let me continue. The interaction is defined like this. And we would like to define dynamics out of interaction. Therefore, we would have to, in order to do that, we have to require some good property to interaction. So, for example, the simplest condition we can require is that for this kind of thing, that is uniformly bounded finite range interaction. That is more precisely, finite range means that there is some natural number m such that phi x is equal to 0 for x with diameter larger than m, and uniformly bounded is literally uniformly bounded by in this sense. And in this talk, what is important is trivial interaction, which is boring thing, but it's important to remark what it is. And by trivial interaction, it is on-site interaction. Namely, if in a kind of interaction where phi x vanishes if this x contains more than one point, that is interaction, on-site interaction. So that was about interaction, and given some interaction, we can define dynamics. We define dynamics out of it, and namely, First, to do that, we construct local Hamiltonian. It is namely for each finite subset, we collect all the interaction term inside of lambda, and then we get some local Hamiltonian. And with this local Hamiltonian, we consider the Heisenberg dynamics and take some dynamic limit, and we get some dynamics. And we take some dynamic limit, but when interaction is of good property, has good property like uniformly bounded finite range interaction, then this limit is known to exist and defines the dynamics on the quantum spin system. The reason for doing that is that we cannot take the thermodynamic limit of this local Hamiltonian, but we can take the thermodynamic limit of time evolution that we can do. So in this operator algebraic framework, we consider not Hamiltonian, but we talk about, instead of Hamiltonian, we talk about dynamics. And the same thing happens in the definition of ground state. So we define a ground state in terms of time evolution. So let me define ground state. So let delta phi be the coordinator of the dynamics. And a state omega on A is called alpha phi ground state if this inequality holds for any element A in the domain of the generator. So it may look a bit strange condition to ask for ground state, but if you consider this condition in finite system and consider if you consider this condition in finite system, you will find that actually this condition is equivalent to our usual ground state definition of ground state, namely a state whose support is under the spectral projection of lowest eigenvalue of Hamiltonian with lowest eigenvalue. So this definition coincides with usual ground state in finite dimensional system. Therefore, we take this condition as a definition of ground state in this operator algebraic setting. And so that is ground state. And I said in the beginning that we are interested in unique capped ground state, Hamiltonian with unique capped ground state. So let me specify what I mean by unique capped ground state. So in general, there can be many states satisfying this condition, namely there can be many ground states. But the situation we are interested in is the case that such a state is unique. So we are interested in unique, is a case that there is unique ground state. And let us consider such a situation. And then we say that this interaction phi has a unique capped ground state in the bulk if there exists a strictly positive number gamma satisfying this condition for all A in the domain of a generator whose expectation value is 0 with respect to the ground state. So again, I'm defining some gap condition by strange inequality. But again, if you consider this condition in finite system, you will find the usual thing that is this condition is equivalent to the Hamiltonian, the condition that lowest eigenvalue of Hamiltonian is non-degenerated, and the gap between the lowest eigenvalue and second lowest eigenvalue are at least gamma. So so it coincides with our usual capped ground state notion. Therefore, we take this as a definition of unique capped ground state in this operator algebraic framework. So that was unique capped ground state. And I said that in this talk, I would like to talk about on-site symmetry. It is quite as usual. So let G be a finite group, and let U be a unitary representation of G on CD. So let beta be an action of G on A given by this adjoint action. It's quite usual. So literally like this, we define action of G. This is our group, our symmetry we consider in this talk. And we say interaction phi is beta invariant if each interaction term is fixed under this action. So if each interaction term is invariant under this action, then we say this interaction phi is beta invariant, and we are interested in such interactions. So that was on-site symmetry. Now I can move to a classification problem. And first, I would like to specify what I mean by the classification of gapped Hamiltonian without symmetry. In this problem, in this classification, what we consider is uniformly bounded finite range interaction within a gapped ground state. That is our objective we would like to classify. And we would like to classify it with the following criterion, that is, two interactions are equivalent, and I write like this. If there is a smooth path inside of this set connecting them. So that is a criterion. So it is some classification. So it's so that is a classification I will consider in the classification problem of unigapped Hamiltonian without symmetry. But here I need some remark. Here I said smooth, but by smooth I require a bit more than just word smooth. Namely, I require there is no phase transition along the path. So let me explain more precisely. I require this three conditions to be satisfied along the path. So let me more specify a little bit more what I mean by smooth. So first of all, we are considering some paths. So so we are considering some paths. So let's say it's parameterized by some 0-1 interval. So for each S, there is some interaction phi S, which is inside of this set. This set. So each S, we have some interaction from here. And first condition says that the following, for each finite X fixed, we get some path of a matrix valued function on 0-1 interval, and we require that this should be smooth. That is one requirement. And second requirement is that the gap is uniformly bounded from below by some strictly positive gamma along the path. This means that now again, this phi S belongs to this set. So this set. So this is gapped interaction. So there should be some strictly positive number gamma S which satisfy this gap condition. And the requirement here is that this infimum of this gamma S should be strictly positive. So the gap should be uniformly bounded from below by some strictly positive constant. That is the second condition. And third condition is about the expectation value of observable. And so again, our interaction is in this set. So it has unique ground state. So let us call it omega phi S. And so let us call it omega phi S. Then for each observable A, there is a path of, we get a function by considering the expectation value of A with respect to this ground state. We get something like that. And the requirement is that when this A is fairly local or sub-exponentially localized element, then this path should be regular in the sense that this function should be differentiable and derivative is not to be compared to the size of this A. So it's a bit vague, but to specify these things more precisely, I need to introduce various norms of elements of sister algebra, which I prefer not to do that now. But I can reassure you that so the third condition may look a bit artificial, but and it actually comes from technical reason. But I can reassure you by saying that these conditions are satisfied if you consider smooth path of Hamiltonian smooth path of smooth path of finite, smooth path of uniformly gapped Hamiltonian in finite system and take thermodynamic limit, then these three conditions are automatically satisfied. In this sense, at least physically, requiring these three conditions is not, it's rather reasonable, I think. So I'd like to do that. So in this talk, when I say smooth, what I have in mind is this. So that is a classification of a uniform, classification of Hamiltonian without symmetry. And as I said, what we consider in this SPT business is the following trivial phase. Namely, we consider this set of uniformly bounded finite range interactions with unique capped ground state, which are equivalent to a trivial interaction. Throughout this talk, when I write phi 0, it means trivial interaction. So what we are interested in is unique capped ground phase, interaction with unique capped ground state, which are equivalent to trivial phase, trivial interaction. So I call this set trivial phase in this talk. So in this SPT business, we consider this kind of thing. And now we introduce the on-site symmetry to the game. So what we consider is the following set that is a trivial, that is elements in this trivial phase, interaction in this trivial phase, which are beta invariant on-site, which are invariant under this on-site symmetry. That is the kind of thing we consider in this talk. And then this is the object we are interested in. That is the object we would like to classify, and we would like to classify them with respect to the following classification criterion. That is, to the interaction phi 0 and phi 1 from this set are equivalent, and I write like this with the beta here. If there is a smooth path inside of this set connecting them, so that it's the same as before, but the inside of here means that the path along the path, the symmetry should not be broken. So that is important point. So this path requires symmetry not to be broken. So it's finer classification than the original this classification. Therefore, this set may split into, in general, this set may split into multiple equivalence classes with respect to this final classification. And the resulting equivalence class is the SPT phases, symmetry protected topological phases. That is a definition of SPT phases in our operator algebraic setting. And that is what I'd like to think about. And in this talk, the question I would like to ask in this talk is the following. How can we distinguish that, how can we say that two interactions belong to different equivalence class or different phases? How can we say they belong to different phases? That is a question I'd like to ask in this talk. And natural approach for doing that should be define some index on this set we are interested in and show that this is actually an invariant of our classification. So if we can do that, then if we say that we can show that the index takes different value from with this and that, then we can say that they belong to different equivalence class. So that is a natural approach to carry such a problem out. And actually, indeed, that is what physicists thought about. And based on what they did is based on analysis on tensor network or TQFT, they conjectured that for no-dimensional quantum spin system, there is a nu plus 1 group cohomology valued invariant for the classification. That is what they conjectured. So let me briefly recall you what was group cohomology. First, ice chain is a function on this direct product of G to U1 phase. And we define ice differential DI as a map from here to there, which is defined like this. And the kernel of this DI is the ice called ice cocycle, and image of DI minus 1 is coboundary. And with respect to the pointwise multiplication, this becomes a group, and this becomes subgroup of this. And so therefore we can consider the quotient, and that the ice group cohomology is the quotient group we get by this. Anyway, whatever it is, there is something, some group, and we physicists conjectured based on the tensor network or TQFT analysis that for no-dimensional quantum spin system with on-site finite group G symmetry, there should be invariant which take value in this group cohomology. And that is a conjecture they made. And main result of this talk is that the following, that we proved their conjecture affirmatively for spatial dimension 1 and 2. That is the main result I would like to talk about today. Okay, so for the rest of the talk, I would like to tell you how to find this group cohomology valued invariant. In the rest of the talk, I talk about how to find it. So let me start from one-dimensional case.
And just this question about dimension 3. In dimension 3, it's not proved, or you expect it's not true?
No, I just didn't go even try. So yeah, I think it's true. Yes.
Thank you.
Okay, so I'm sorry, but today what I can say is only up to two-dimensional system. So okay. So let me start from one-dimensional system. According to physicists, we should be able to find second cohomology class valued invariant here. And how can we find such a thing? But then we recall that it is well known that the second cohomology class shows up naturally from projective representation. So projective representation was something like that. That is a map from group to unitaries of unitary operators satisfying these relations. And so it is almost like group representation, but there is some U1 phase, which is obstacle. And it turns out using this the associativity of U's, we can show that this U1 phase satisfies two cocycle relation, namely, it belongs to this kernel here. Therefore, taking this quotient, we get to a second cohomology class. So, so what I wanted to say is when we find we have projective representation, second cohomology class naturally shows up. Therefore, the goal seems to be to find some projective representation in our system. But actually, this projective representation was already there from before. This is thanks to a great result by Matsui on split property. What he said is the following. What he showed is following. Unique capped ground state satisfies the split property. So split property is some property of state, saying that roughly speaking, it says that the state is almost like product of two left infinite state on left infinite chain and right infinite chain. That is roughly split property means. I will not define the split property in this talk precisely, but what is important for us in this setting is that with split property we can find projective representation. That is something even from far before, like around millennium, this thing was known from before. That is, a projective representation can be associated naturally to beta invariant pure split state. But there is this fact. So, and recall that what we are the interaction we are interested in is beta invariant and with unique capped ground state. So our unique capped ground state is beta invariant because phi is beta invariant and phi, omega phi, our ground state is unique ground state. So it should have to be beta invariant. And so, for the same reason, it is pure. And it satisfies split properties thanks to Matsui. So we were in this situation. So combining these two, there was a projective representation was already there from before. So what I did is I just picked up this projective representation and considered this corresponding second cohomology class. And what I showed is that this is actually an invariant of our classification. So things went well in one-dimensional system. And as a physicist said, there is a new second cohomology valued invariant in this SPT phases in one-dimensional quantum spin system. So things are great there. So having that, now I want to think about higher dimension. So so I decided to start from 2-dimension. And so how about 2-dimensional case? Then immediately we face some problem. That is lack of this great result by Matsui. That is, we do not have any split property. Any form of split property for unique capped ground state in 2-dimensional quantum system is not known. At least I do not know. And even actually, to be honest, even if it was known, a priori it is not clear for me how to use it to define an index. So I faced some problem. Then I decided to take the advantage of the situation of the problem. So what is the advantage of the situation of the problem? That is, we are considering only symmetry protected topological phases. Recalling this, the definition of this set, it was trivial phase with respect to this classification. So what we are considering is not general unique capped ground state, but what we are considering is the ones which can be connected to trivial one. More precisely, let us fix some trivial interaction with unique capped ground state. So I will fix this phi 0 all the time. And its ground state is of product formed by a definition, because this is on-site interaction, so ground state is of product form. So we fix this trivial interaction, and then by definition of this set, for any element of this inside of this set, is equivalent to this trivial interaction with respect to this classification. Namely, if we do not require the symmetry to be preserved along the path, they can be connected. That is the situation we had. And actually, this is quite a strong, quite a good situation, easy situation, because this immediately means that our ground state omega phi has a short range entanglement. And this implies that omega phi has a short range entanglement. And we can say that thanks to the strong machinery called automorphic equivalence. So let me next explain what is automorphic equivalence. Automorphic equivalence started as Hasting adiabatic lemma, and after seminal mathematical development by Bahama, Mikalakis, Nahteugiel-Sims, and Nahteugiel-Sims-Young, we have now a great, it now become a great strong machinery to analyze gap ground state phase in quantum spin systems. And remark is that the machinery was developed was about taking thermodynamic limit type of theorem. But as I said, I insisted in the beginning, we needed some. I wanted to start immediately from infinite system, so I needed some infinite version of the automorphic equivalence, and with Alvin Moore, we extended it to infinite system. Anyway, so actually what we use here is this one, but anyway, we rely heavily on the history. Anyway, so let me now explain what is automorphic equivalence. It says the following. Let us consider the smooth path of interactions in unicapped ground state phase. Then it says that there is a smooth path of automorphism alpha S satisfying a concrete differential equation given by some time-dependent local interactions which satisfy this condition. Namely, given some smooth path of gapped Hamiltonian, smooth path inside of a unicapped ground state phase, like we do for our classification. In this situation, there is an automorphism interpolating the corresponding ground states like this. But it's not only just interpolating the ground state, but actually we know a lot about this alpha S. Namely, it satisfies some concrete differential equation, and the differential equation given in terms of local interactions. This is quite a lot of information, and this enable us to do many things. And in particular, in our setting, what is the property which is important for us about this alpha S is that because it is given by a local interaction, we can cut this alpha S and factorize it. That is very important for us, and this turns out to be very useful in our analysis. So let me explain what I mean by we can cut alpha S and factorize it. And first, let me start from one-dimensional system. So we consider a one-dimensional system. One-dimensional system. There is origin here. So in one-dimensional system, the factorization property can be written like this. Alpha 1 is decomposed to automorphism on the left infinite chain and right infinite chain and something inner. So in this talk, when I write inner, it just means adjoint of unitary with some unitary in the quantum spin system. So I do use this notation. But anyway, the factorization property means that alpha 1, our automorphic equivalence alpha 1 factorizes to left some automorphism localized here and some automorphism localized there, and some inner automorphism, which is something like that with possible test. So that kind of a factorization we can carry out in one-dimensional system. So in two-dimensional system, we can have the following factorization. Namely, first I split the plane into two, to left half plane and right half plane. And then according to this split, alpha 1 can be split into a left infinite half plane part and a right infinite plane part and some error. So in this case, this alpha L is localized in this half infinite left plane, and the alpha R is localized in this half plane, and then this xi is almost localized along y-axis. This is an error which occurs. But this gamma of this xi is not really strictly localized, but they tail along y-axis. And we can do this kind of decomposition, but we can remove tail if we allow the cut to cut it with cone. So let's consider any angle theta, and we consider this kind of a cone. Then we can split gamma, xi to something inner and something strictly localized in this cone. So this theta is strictly localized in this cone. We can do this kind of decomposition. So that is okay, but what's the use of it? You may wonder. So in order to convince you that this kind of factorization property can help us to find the group cohomology valued index, I would like to demonstrate proof to demonstrate a derivation of second cohomology class in one-dimensional system using this factorization property. Okay, let me do that. So recall that our situation is that something like this. So our ground state of in SPT phases of phi in SPT phases, it can be given by automorphic equivalence, namely by from some product state times some automorphism which has some factorization property. So we are in this situation, and this omega phi 0 because this is tensor just product state. So in particular, we can split this to left infinite chains pure state and right infinite chains pure state. Both are pure state. And furthermore, because our ground state is beta invariant. So let us write this beta invariance condition here. So our ground state is invariant under beta. Now I substitute this decomposition and this decomposition and this equation. So substituting them, what we get on the right hand side is omega L alpha L tensor omega R alpha R times something inner. And similarly, on the left hand side, what we get here is omega L alpha L beta G L tensor omega R alpha R beta G R and inner. Here beta G L is the restriction of beta G to left infinite chain and the same for right infinite chain. Okay, like this. So I change the formulation a bit, and then we have this is equal to this state times something in. We get something like that. Now we recall some basic fact from operator algebra that is written here. It says the following. So let omega L, omega R be pure state on left infinite chain and right infinite chain. That is the case for our omega L and omega R. And this is the GNS representation of this state. Then let alpha L and alpha R be automorphism of alpha on left infinite chain and right infinite chain. So in our case, this alpha L means this one, and alpha R means this one. So let us we have the situation here, and then the assumption of lemma is that suppose that this alpha L, alpha R, and omega R, omega alpha R should satisfy this condition. That is, this tensor is equal to this tensor modulo inner action. So that is the assumption of the lemma, and actually we are in this situation here. Then the lemma tells us that under this condition, this alpha R can be implemented by unitary operator on this GNS representation of omega R. So there is some unitary operator UR which implement this alpha R in this sense. That is a general lemma, and we are in the situation we can apply this lemma. So let us apply this lemma, and applying this lemma, we get some unitary on GNS representation of omega R, such that which implement our automorphism, which is this one. We see that this is the situation. So applying this lemma, we get some unitary which implement this automorphism on the GNS representation of omega R. And you see this is a group action, and furthermore, this is irreducible representation. This means immediately that this UGR is projective representation. And actually, this is actually the projective representation we used to define the second homology class index in the one-dimensional SPT business. So this is the very projective representation we considered in one-dimensional system to define the second cohomology class invariant. So what I wanted to say here is using this factorization property allows us to have a handy way to define some the group cohomology valued, second cohomology valued invariant in one dimension. Having that, we get a hope that there may be a possibility that in fact, this factorization property may help us to find third cohomology valued in index in two-dimensional system. That is what I wanted to say in this slide. I hope it worked, but yeah. Anyway, so having this kind of consideration, I decided instead of considering speech property in two dimension, I decided to use this factorization property to define our index. That is what I wanted to say. Oh my God, I don't have any time actually. Oh. Sorry. So still we have to find some third cohomology class somewhere. And actually there was, so in one dimension, the second cohomology class came from projective representation. And in Harvard two-dimensional, how can we find third cohomology class? The inspiration came from operator algebra business on group action, and there they naturally find a third cohomology class. So let me explain what it is. In their setting, they consider a set of automorphisms or a factor. Factor means a phenomenal algebra with a trivial center. And they consider automorphism satisfying this kind of conditions. And using associativity, we can derive that there is some phase factor satisfying this relation with this given U. And so it's very basic calculation, but I skip it because I don't have time. And it turns out this phase satisfies three cocycle relation, and like this we get some third cohomology class. Okay, so what I wanted to say is that from operator algebra literature, we can see that if we find some set of automorphisms satisfying the following, that is, this combination become inner given by some unitaries, then we can immediately get some third cohomology class. That is something we can learn from operator algebra literature. But how can we find such a thing in our setting? That's a problem. But the hint for me came from former works of index of gapped phases. The hint so the thing is as follows. In these former works of index of gapped phases, the basic principle is to cut the system into two. That is, for example, in bulk edge correspondence in free fermion, the bulk edge correspondence free fermion tell us that to cut the system into two. If you want to know about bulk, you should cut the system into two and look at the edge. That is what they do. They say, and that is the same kind of philosophy was used in quantum spin system as well. Therefore, for me, it was rather natural to think about to cut the system. So I decided to consider the action of G restricted to a half plane. That is, I decided to consider this action of G. And then I made some very simple observation on very simple model, very nice model which is related to digraph Witten model, there are, I considered this kind of, the situation is as follows. Like in automorphic equivalence, the ground state is given by product space times some nice automorphism, and this automorphism satisfies some nice factorization property. Namely, if we consider this kind of object, then it's split into left to right like this. And I observed that by this, from this, if our automorphism alpha 1 satisfy this condition, then we can obtain the, we get to the situation operator algebraic thought. Namely, if we consider this gamma g, if we define gamma g by this times the action beta ur, which is action of ug on this side, this area, if we set this, then this combination become inner. And this is a really simple observation that because this is, you can see that from this equation immediately. So what I wanted to say is that if we have this, if our automorphic equivalence satisfy this nice equation, then we get some third cohomology class. The problem is that I don't know if this alpha 1 in general satisfies such a nice condition. However, it turned out that some weaker version of this condition can be satisfied in our setting as well. And it turned out that that is enough. And we get, although we do not get our gamma g is not inner itself, but it can be implemented in suitable Hilbert space by some unitary operator, and this unitary operator do the job and to give us some third cohomology class. It turned out to be so. So like this, I'm sorry I didn't really explain, but we somehow managed to define third cohomology class valued invariant. And as you notice, in order to define it, I used mainly the automorphic equivalence, we used this alpha 1, but in general, there can be many ways to connect our interaction to the trivial interaction. But so there is many ambiguity, like choice of alpha 1, and also for factorization property, which I used to define the index, but this factorization, there is ambiguity of the choice of the angle, with which angle we cut the automorphism, and there is also ambiguity about this operator etas as well. Okay, so the index was a priori defined based on many things, but it turned out that it is independent of any of such choices. And most important thing for us is that this is actually an invariant of the classification of the SPT spaces. Okay, sorry, I didn't really couldn't really explain the last part very well, but that's the end of the story. Thank you very much for your attention.
Thank you.
Oh, thank you very much. I'm very much impressed. So any questions, comments, please? I have some, but.
Well, I have a question, if I may.
Sure.
So yes, the hour was too short, Yoshiko, to explain everything, and so, but I'm of course very intrigued by, in particular, the last 10 minutes of your talk. So I was wondering, it made me think of this line of research initiated by Peter Nijkens in which in a study of Kitaev's quantum double models, where he uses an extension of the cone algebra by some unitary or other operator that seems to be very reminiscent of what you introduced. So can you comment on that? I mean, I haven't had time to really think about it.
I didn't really thought about it, but I have an impression that this sector theory can have different way of describing things in nicer way, maybe. So, but I never really thought about it, so I cannot answer.
Maybe it's something to think about. Or maybe Peter has comments. What would you say, Peter? Didn't it?
I mean, it's so I mean, it's actually sort of related to a question that I had, because so you really use that you are in the trivial phase, right? So the Tor code model is not in the trivial phase, so yeah, you don't have the split property for sure, but like a weaker version. So yeah, I think it's not so clear indeed how to define such an index. I mean, I guess you can imagine like putting a symmetry on top of a sector structure and see if you can get like a finite classification. But I think what Yoshiko said is it's not so clear how to actually do that. Yeah, but yeah, this picture that you had with this half planes and this kind of cone, that's kind of similar indeed. But yeah, I don't think I have much more to say about that at this point.
Any questions, comments?
I wanted to ask, what is short-range entanglement?
Yeah, actually, I'm not sure, but by that I just mean that it can be connected by the automorphic equivalence, which is given by local elements, local interaction. So I don't know if it is the correct definition for short-range entanglement, but what I mean by here is this relation holds with this one being a product state.
Okay, thank you.
Yeah, so let me add that this condition is necessary from physical point of view. In 2 dimensions, you have something called topological order, in which people believe that there is long-range entanglement. And this SPT business is to classify something which do not have this topological order. So her condition is not something mathematical, but this is really physically important. Any other questions, comments? Yoshiko, I wanted to ask the role of this cone. So when I think you said that when you analyze this simple model of Digraph-Witten, then you only needed to cut the system into 2, and you could sort of derive this third group cohomology. But so you didn't need any cone in this case of Digraph-Witten, or did you?
Yes. So just in general, the models are not as nice as Digraph-Witten, that we have to deal with it. And
so first of all, so when you deal with simple model like Digraph-Witten, you don't need this cone.
No.
Am I right?
No. Yes, you're right.
And when you wanted to treat general class of models, then you use this cone.
Yes.
Instead of simply cutting the system into 2, you first restricted the system into this cone region and then separate it, or?
What is important for me is to get some automorphism which is strictly localized in some specific area. That's a fact I use repeatedly to define the index. And considering cone is one way to do that.
So if I may follow up on that, so is this basically because you have a non-zero Lie-Robinson bound? That's why you need to go? No. Yeah. Okay.
Any questions?
Can I ask a question about the three-dimensional case? So in that case, physicists think that there are these beyond cohomology states, especially in cases with time reversal symmetry. And I was just wondering if you could see that maybe some additional mathematical structures would show up in that case that would take you beyond the group cohomology classification.
Sorry, I really haven't done anything about even didn't try. I just finished 2 dimensions. So I don't know. I cannot answer this question. Sorry.
Okay, no problem.
Yeah, but that is very interesting. So I wanted to ask this to an expert. So Matthew, are you an expert on this? So I hear that.
Yeah, go ahead. Go ahead.
Yeah, so I hear what I learned vaguely is that they are talking about different classification using cobordism or something like that. And they say that, well, this group cohomology works in some case, but the better classification is given by cobordism or whatever. So I wanted to know the consensus of physicists. Because of course, even Yoshiko can prove something which is true. So,
well, I know that in 3 dimensions is the first case where there are these extra phases that seem to show up, and it's in particular in the case with anti-unitary symmetries like time reversal. I know that, so there's this work by Kapustin where he proposed these cobordism groups as an extension of the classification. They seem to get the counting right. But yeah, so I'm not an expert in the justification for that, counting according to those groups. But yeah, no, it'd be interesting to see if, certainly people suspect that there are these states beyond cohomology when you get to 3 dimensions and above, but I don't think the exact classification is known. Or starting from first principles, like in this work.
Good. Any other questions? Oh, actually, I was talking to Yoshiko about this kind of problem, but I still cannot believe it that you have this already. So it seemed to be so difficult.
Yeah, but it's a bit of kind of cheating to use this short-range entanglement.
Oh, but yeah, but that is the rule of the game, right? So
yeah,
especially in 2 dimension. In 1 dimension, probably, of course, that is something you have to prove, but in 1 dimension, you have better results. So yeah, so I think you're not cheating at all. Yeah, this is great. Any other question or comments? Okay, so I think we can close this formal part by thanking Yoshiko for this wonderful lecture at the end of the year. Thank you very much.
thank you for attention.
Thank you.